Here's a problem on satellite motion for an elliptical orbit. This is from the AP Level C Mechanics exam from the year 1994. This is problem number 3, and we're told that a satellite with a mass of m is in an elliptical orbit as shown by the dashed line in the diagram, and when it passes point A, it has a speed of v0. So let's draw that in. When it's at point A, speed is v0. Okay, and then it's going to follow this elliptical orbit and at some point reach position B. Part A, we have to write a definite integral in order to show that this equation satisfies an expression to calculate gravitational potential energy based on a reference level such that gravitational potential energy equals 0 when any mass is infinitely far away from the center of the Earth. So without solving it, we just have to write the definite integral. Change in gravitational potential energy is equal to negative work done by a conservative force. So this is equal to negative the integral of negative gmm over r squared dr. And from the limits of infinitely far away to whatever position the satellite happens to be at. The negative signs then cancel out, and so we just have to evaluate the integral of gmm over r squared dr. And that's good enough. Write the definite integral that can be evaluated, but no instructions are given to evaluate this. But we know if we evaluate it, we're going to get this as the final answer. Part B, determine the total energy when it's at position A. So at position A, it's got kinetic energy associated with the motion, and it also has potential energy based off of this equation. So the total mechanical energy is the combination of kinetic and potential. So the total mechanical energy is 1/2 mv0 squared minus g m times the mass of the Earth over, well, over what value? Its distance when it's at point A is just labeled as lowercase a. So minus gmm over a. And that's as far as we can go without any numerical values given. We're just told to answer in terms of all of these quantities: a, b, lowercase m, mass of the Earth, radius of the Earth, v0, and g. So in our expression, we have all of the quantities that we're allowed to answer in terms of. Okay, so part C. What's the magnitude of the angular momentum of the satellite when it's at point A? So again, draw in speed v0 has a mass of m. Oh, well, angular momentum is just the cross product of linear momentum and distance. Actually, I think I have that backwards. I think it's r cross p. In magnitude, that just means angular momentum is r multiplied by mv. So in this case, it's equal to what? R is the same thing as a, and v is v0. So there you have it. That was easy. D, determine the velocity of the satellite as it passes point B. Well, this quantity angular momentum is conserved, so the angular momentum at position A has to equal the angular momentum at position B. The angular momentum at position A is m v0 a, And so the angular momentum at position B, if we just write in another velocity vector, we know it's going to be traveling slower here based on the law of equal areas, so we'll just call this V as opposed to V naught. So this is mv b, m cancels out, so this velocity v is just a over b times v naught. Simple enough. Then we're told as the satellite goes from point A to point B and then continues on from point B back to point A, when it reaches point A again, a rocket engine is fired so that its orbit is changed to a circular orbit with a radius of A. Determine the speed of the satellite for that orbit. Well, okay, for a circular orbit, gosh, we've seen this a lot. I'll write it again. Centripetal force is provided by gravitational force. So mv squared over r is equal to g mm over r squared. That allows us to cancel out the mass of the satellite, and all that matters now is the mass of the attractor. And v is equal to the square root of g m over r. Now, to answer in terms of the variables given, then the speed for this circular orbit, we'll call that v subscript c, is equal to the square root of g, mass of the Earth, divided by a. Part F. Determine the amount of work done by the rocket to effect this change. So work is equal to the change in mechanical energy. So the work is equal to we got to take this expression, that's the total mechanical energy when it's at point A in an elliptical orbit, and then subtract from that the kinetic energy it would have, or the total mechanical energy when it transitions to a circular orbit. So this is going to be 1/2, well here, how about we just write this? Kinetic energy for the elliptical orbit plus potential energy for the elliptical orbit minus kinetic energy for the circular orbit plus potential energy for the circular orbit, comparing at point A just before the rocket is thrusted to point A just after the rocket thrust. So the potential energy and at point A just before the rocket fires and the potential energy just after is the same because we're referring to at position A, so that's going to cancel out. So we really just need to find the change in kinetic energy. So this is 1/2 m v naught squared minus 1/2 m square root of g m over a quantity squared. So the work is 1/2 m v naught squared minus 1/2 g m over a. And then without being given any numerical value for this v naught, I think that's as far as we can go with this expression. So there you have it.